Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel. Good day, everyone. Last episode, we talked about work and energy and power and energy conservation. Now, let's talk about heat energy. Well, before we can talk about heat energy, let's talk about temperature because temperature is kind of like an embodiment of heat. Heat is a form of energy called thermal energy. So that when we place a pot of cold water on a heating stove, after a few minutes the water feels hotter to the touch. Now the reason why the water feels hotter is that the um the stove has transferred heat, and when time you transfer heat to an object, you are increasing the temperature. So kind of temperature is kind of like the change in the heat of the substance. When the change in the heat is positive, you have an increase in temperature. When the change in the heat is negative, you have a decrease in temperature. So when you are comparing the kind of, we want to talk about temperature itself. Temperature is kind of like the hotness or coldness. Is a relative okay, we can't call it relative heat now because heat, when you talk about something that's the heat of a substance, heat is energy, while temperature is kind of like a degree of hotness or coldness. So temperature is quite different from heat. It can't be interchanged because a cold object which is more massive than a hot object, if you see a cold object, maybe like a large amount of water which is cold, it might have more heat than a small amount of water which is hot. So it just depends on the concentration of the heat energy. So if the energy is dispersed, or if the object has a wide volume that the heat is dispersed, then the temperature will be low. But if the heat is concentrated, then the temperature will be high. And when we moved on to consider it in a subatomic frame of understanding, we'll notice that the heat is actually an embodiment of the kinetic energy of the particles. So we'll still say that there's a linkage between kinetic energy and heat energy. Now, heat of a body, it has different outcomes on that body. For example, it can cause a change in temperature of the body, which we discussed earlier. It can also cause a change of state of the body. So the body can change state. This is common when you heat water to the boiling point. It changes states from liquid to vapor. Then we also have the expansion of the body. So even water as itself, above 4 degrees, water expands as you heat it. So this expansion is as a result of the heat that is applied to the body. Then we also have change in physical properties of the body. Yes, something like magnetic property. When you want to demagnet a piece of iron, you can heat it to a very high temperature, and then you alter the atomic positions and energy states of its subatomic particles, and then as a result of that, you have kind of gotten rid of their magnetic potential energy. Then fifth, we also have thermionic emission. Um, Actually, thermionic emission is basically the addition of heat to a metal, which may result in the emission of electrons from the surface of the metal. It's also called thermionic emission, and it is usually applied in various parts of physics. You make use of thermionic emission when you want to produce if if a fast stream of electrons, and that is used in a kind of like a cathode ray tube. So those stream of electrons, they they actually have kinetic energy, and they are caused they are emitted by the heated metal. Even whenever you have something like an X-ray tube, X-ray tube also applies basically on the principle of thermionic emission, and which is that when time you have a high temperature, electrons are always emitted because the electrons will kind of have enough energy to escape from the surface of the metal. It is analogous to the concept of evaporation, kind of like when you heat water to a very high temperature, the particles of the water molecules will acquire enough energy to escape, and that is what is the result of our rain cycle and precipitation. So we also have change in state, change in chemical properties, which is chemical change, and change in pressure. So when you heat the substance, you increase the temperature, and it also affects the pressure. Now, in a certain stage of this video, I talked about atoms and all the rest. Now, it wouldn't be proper for us to continue ranting about heat energy without talking about the atomic nature of matter. So, the molecular theory of matter assumes that matter is made up of atoms that aggregate in molecules. So, that is called the kinetic molecular theory. Now, the atom is a small particle of an element that can have a separate existence and still retain the chemical properties of that element. So, you can actually separate and isolate an atom of a substance, and it will still give you the chemical properties of that substance. So, and it is basically the smallest particle of a substance that can actually take part in a reaction, because since it has the chemical properties of that matter, so it can also participate in a likely chemical reaction. Then we also have the molecule, is a group of atoms of the same or different elements joined together in a simple proportion. They can also be made up of atoms, because those molecules, they themselves are like aggregates of atoms. So when those atoms come together to form molecules, they have a new chemical property which is caused by the chemical reaction. So now that's the basis of kinetic molecular theory. And this theory, it assumes that every substance is made of a particle called molecules. It also assumes that the molecules are in a constant state of random motion, which are colliding elastically with one another and changing their direction as a result. So these molecules, they are not static, they are actually moving together. They are moving at very, very high speeds. So that is the second postulate of the kinetic molecular theory. Then also that there's always an attractive force between the molecules. So that is basically in matter, in most matter, there's always an attractive force between particles of matter, but the only thing that changes is the degree of attraction. The next, finally, we also have that the volume of the gas molecules is negligible compared with the volume of the container. So because gases, in the kinetic molecular theory, we know that gases, their particles are widely spaced. So, and we know that the space between those particles is actually related to the density. That is why solids are very dense. You can, when you try to heat a solid, it can't. Most of the time, they don't feel way. Kind of like a wooden. If you hit a wooden table with your fist, you can't break the table that way. But if you kind of hit through air will just slide the air molecules will slide around your hand, which will pave way for your hand to move through. So had it been air was as dense as wood, that means we wouldn't have been able to kind of move about, or maybe we would, even if we would need a lot of energy to do that. Now let's specifically consider one effect of heating an object, which is the expansion of the object. And we are going to be talking about linear expansion. Linear expansion is basically the expansion of an object when considered in a straight line. So when you consider the expansion in just one dimension, which is straight line. So for us to understand linear expansion, we first need to know what linear expansivity is. So, and that is the increase in length per unit length per degree rise in temperature. So what this means in symbol is equivalent to linear expansivity, which is alpha equals L2 minus L1, L2 minus L1 divided by the product of L1 and the change in theta. That's theta 2 minus theta 1. That will be equal to L2 minus L1 in the numerator is equal to the expansion, then divided by L1 times change in theta. That's L1 theta. Here the L1 is the length of the metal at the temperature of theta 1, and the L2 is the length of the metal at temperature theta 2. So what this means is that the length is actually changing at different temperatures. Now let us discuss some consequences and application of expansion. One consequence and application of expansion is in the expansion of building and steel bridges. So for example, if you have this building, this steel bridge, now this metal expands as the temperature of the atmosphere rises. It also it also gives it heat, and also the temperature of the metal which is used in construction of this bridge, it increases, and so the metal expands. So that means there needs to be some form of mechanism to kind of offset it and kind of offset the expansion. So that's why they make use of extension gaps. So extension gaps, you have a fixed end and you have an extension end. So this is one of the ways engineers apply the knowledge of expansion to kind of read everyday life. Another demonstration of expansion is in the expansion of your railway lines, because these railway lines, they are also metals, and because of this expansion, gaps are left between the rails in the railway lines to allow for free expansion and contraction of the rails. So without the gaps, the rail joints will swell up on hot days, and the rail line will buckle and trains will be derailed. So that's why you have these gaps, and in these gaps you have nuts and bolts, and so these nuts and bolts, they slide in these gaps. So when the metal expands, they slide to the direction of the expansion, and so they reduce the tension and tightening forces, so that this these railway lines can operate at all temperatures. Before we move on, let's continue and talk about the area of superficial expansivity and the volume or cubic expansivity. So the area expansivity is very similar to the linear expansivity, in that is the increase in area per unit area per degree Kelvin rise in temperature, or is also known as the fractional increase in area per Kelvin rise in temperature. Our volume expansivity, instead of area, it deals with volume, so it is the rise in the volume of a substance per unit volume per Kelvin rise in temperature, or the fractional increase in volume per Kelvin rise in temperature. Now, by experimental analysis, it has been proven that the area expansivity is twice the linear expansivity, and the volume expansivity is thrice the linear expansivity. So there's a relationship between them, and it's often used to calculate either of each when you are given any one. When talking about the expansivity, the volume expansivity, in real life, we don't basically measure fluids on their own volume of liquids. We measure them inside containers. So, and then we carry experiments in those containers, and those containers, they have their own expansivities. So anytime you are looking for the expansivity, you use what is known as the real expansivity, which is equal to the addition of the apparent expansivity to the expansivity of the um, container used to measure or contain the fluid. So real expansivity is the sum of apparent expansivity plus expansivity of the container. Now, one notable effect of application of heat on substance is the change of state, and this change of state, they occur through different processes. An example of such processes is fusion. So fusion is basically the process whereby a substance changes from the solid state to a liquid state when you heat it up. So basically, an example of that is when you have ice, when you heat ice, or you remove it from your refrigerator and you put it on the atmosphere. So the temperature of the air is enough to heat it to beyond its fusion point. So beyond that point, it becomes a liquid. Apart from fusion, we also have vaporization, which is another change of state, where an object changes, or a substance changes from a liquid to a gaseous state when heat is applied to it. So an example of this is when you heat water, it changes from your liquid water to water vapor, which is the vaporization. Then this vaporization, it occurs at a definite temperature in a substance. So we have, it's also known as the boiling point, and this evaporation, it is the second part of change of state. Now let's talk about transfer of heat. There are three major ways by which heat can be transferred, and they are conduction, convection, and radiation. First of all, conduction is basically it's the process by which heat is transferred through a material such that the average position of the particles remain the same. So in this case, even if the heat makes the particles to be displaced from their mean position, the particles will still come back to their equilibrium position. So that's what is the process of conduction, and conduction is very, very common among metals and solids. Now let's talk about convection. Convection is kind of like a heat transfer that's very common in everyday life, and convection occurs majorly in liquids and gases, which are generally poor conductors, but heat is effectively transferred in them by convection, and it involves the transfer of heat by the actual movement of the heated molecules from the hot parts to the cooler parts of the liquid. Convection is the process by which heat is transferred in liquid or gas by the actual movement of the heated fluid from the hotter to cold parts. So a very example of this is what I'll be giving soon. One practical application of or demonstration of convection is when you drop a crystal of potassium permanganate, which is purplish deep purple in color. when you drop it into a container full of water, so after some time the whole water will have that purplish color. The reason for that is not because it's not generally because of the the particles moving, but it's because of convection current. So the particles are moving due to convection current. When this potassium permanganate crystal is at the bottom of the water, the there's a high concentration of those crystals, the molecules at the bottom. So with time, due to diffusion, those the diffusion sets up a convection current. So this convection current, it moves upward and is replaced by the unsaturated part in the upper part of the fluid. So another example of convection current is with that occurs anytime you are trying to boil water. When you're trying to boil water at the bottom, which is very hot, it rises up, and then what the cold water at the top of the container, it settles down. And so due to this circle, it causes a convection current to happen. Another demonstration and application of convectional current in nature is land and sea breeze. So land and sea breeze, they are the result of convectional currents in nature. On a hot day, the sun warms the land more quickly than the sea because the land is a better, but the air near the land warms up and rises, cools the rising air. The convectional current is completed by the action in the upper atmosphere moving down in the opposite direction. The cool breeze that blows inland from the sea is called sea breeze. Now this is sea breeze because it blows inland from the sea. When we talk about land breeze, they are like the reverse of sea breeze. At night, the reverse process takes place, where the sea retains much of its heat than the land in the night. So while the land temperature drops considerably, as a result, the sea is warmer than the land. Convectional current is set up in the opposite direction to the daytime. So that means that the breeze blowing from the land to the sea is opposite that which blows from the sea to the land in the day, and that is known as the land breeze. Now there's a third method of transfer of heat known as radiation. And radiation is the process by which heat is transferred from a hotter to a cooler place without the heating or intervening medium. An example of this is when the sun's um, solar rays are transferred outward to meet the earth. So those rays, they move through space, and space is actually empty. Space is there's no medium. So it's those radiation, they can transfer through space, which is a medium, because they are electromagnetic waves, which are example of that is visible light. So all these waves, they don't need a medium, and they are mostly propagated by the method of radiation. Now, because of our knowledge of the way transfer of heat works, we are able to make new technology as time goes on that kind of combats with each of these transfer methods. Example of this is the thermos flask, and this flask has been designed in such a way that it reduces heat transfer and heat loss from the flask, so that the contents of the flask will not lose their heat to the surrounding, and it tries to minimize this way by reducing conduction, convection, and radiation. So the cap reduces loss by different ways. The thermos flask, the flask has a double walled glass vessel with a vacuum between the walls. The vacuum is to reduce the loss or gain of heat by conduction or convection, and the double walls of the glass vessels are severed on the vacuum side. So this minimizes the loss or gain of radiant heat to the outside. And the bottom of the flask rests on cork supports, and the mouth of the flask is also closed by a cork stopper or a material. And these materials, they are all poor conductors, and because of this, no heat is lost or gained by conduction. So it is designed in such a way that it also prevents heat loss by evaporation and convection if the flask contains heat hot liquid. The glass vessel is also placed in an outer container made of plastic. So because of all these features, heat loss or heat gain by the flask from the surrounding is very, very small.